All right, welcome to today's training video. We're going to cover how to run calibration analysis for calibrating your GC to use with Catalight. And I'm going to show you mostly how to do the analysis part, and then a quick overview of how to work with the GUI to actually capture the calibration data itself that you're going to need to do this calibration. So uh, there's two things that you need to get started. You're going to need to have calibration data that's at least in the format needed to work with the Catalight project. And you're also going to need a calibration file. So to start with, I'm going to show you how you would run this in the GUI. So using the GUI, I've already pre-populated what one of these experiments would look like. So this is a calibration experiment. You could also do this with a composition sweep, and it really doesn't make too big of a difference other than the name that gets generated. You can just create an experiment, and then you're going to want to make sure that you select this calibration file. It'll give you a warning message on the next screen if you don't have one selected. When you create the calibration gas file, and I'll show you what that looks like in a second, what it's doing is it's creating a custom gas mix to run through the MFCs so that you get an accurate flow rate so that you can build your calibration. If we come over to the experiment tab, you can see what a pre-designed experiment looks like that I went ahead and made. So when you select either calibration or gas comp sweep, it's going to change what this independent variable entry looks like. You get all these different options, and to do a calibration, you're going to want to set fixed to two of these. You're going to essentially turn two of the flow controllers off, or if you have a different number of them, set that number to 0. And then whatever MFC system you're running your calibration gas through, you're going to set that to the independent variable. You're going to vary that to whatever parameters you'd like, and then set some inert gas, preferably the one that's the fill gas in your calibration tank. Set that to fill. Make sure you enter in all the other parameters that you can. A note about temperature: if you're running this without the reactor connected or the heater on, this will throw an error if your temperature value that is reading is above 10 degrees of the temperature that you set it to. So think about it this way: of if you were running back-to-back temperature sweeps and the temperature was too high, the system knows that and it wants to wait and cool off before it starts the temperature sweep. So you don't want to artificially tell a reactor system that it's too high of a temperature by whatever number you enter in here. So I usually have the Herrick cell plugged in so that it reads at room temperature, and I give about a room temperature variable within 10 degrees, and it won't throw any errors. Then you can set whatever you want for the rest of these parameters. And the most important part is to make sure that you pick the right gases to flow through. The composition numbers don't matter when you're doing a composition sweep because they're defined up here. But for these gas types, these do matter. So make sure that the calibration gas is connected to whichever one of the MFCs that this corresponds to, and make sure that your fill gas is connected to whatever inert gas that you want to use. Once that's all done, you can go ahead and run the study. And then you're going to collect some data. So I'm going to open up what that data looks like here. So here is where we keep in our group some of the different calibration files. So I'll go into one that I previously ran. And inside of here, you're going to have an experiment folder. Inside of that, you're going to have the experiment log with data and results subfolders. The results subfolder is currently empty. That's where our final computed calibrations is going to be. And inside of the data folder, you have folders for all the different steps inside of this calibration sweep. So for us, we're just sweeping through one calibration gas and diluting it more and more to build our calibration off of that. Now, what does your calibration file look like? So to begin with, you need to put in some calibration file in the form of a CSV. There's more information about this on the Read the Docs page, and you can see exactly what this file should look like. But the most important things to have in at this point is to have some chem ID number, and this should correspond to whatever the gas library is on your MFC. If these aren't listed exactly in the way that they are in your MFC, it's going to throw an error on the MFC system because it doesn't recognize the gas that you're trying to flow. This is taking the top 5 or 6 gases in terms of concentration. It's mixing them together and giving that as the calibration number for the flow controller so you get accurate flows. And then at this stage, it's really important for you to have the concentrations for each of these different gases listed inside with these headers. That lets the code sift through which are present in the highest concentrations, and then it's going to build the custom calibration gas that it uses based off of those numbers. At this point, you don't have to have any of these other parameters filled out, but I did fill out the elution times beforehand. You don't have to do this before you do the calibration, but I want to show you what it looks like and some possible problems that you might see using this. So notice here that propylene and propane are both overlap in the calibration file. And I'll show you that for us, in the hardware that we're using, butane and butene, they're also right next to each other, and we're also using an FID, so we don't even detect hydrogen. You still want to have all of these gases in this original calibration file and their relevant concentrations, just so that it can go ahead and build the calibration gas that it needs to use. And then I have an offline version of Peak Simple here, so you can see what this looks like. So here you see we've got 2 different chemicals that are overlapped when they elute out from the GC completely, and then we've got 2 that are too close to really be resolved, and those are going to throw errors eventually if we were to put in this exact calibration file. So for the next step, I went ahead and used a different calibration file where propylene and propane and butane and butene, I lumped those together as one peak. And I wrote in the calibration file that there's 2 different chemicals inside of these. But notice for the chem ID, I did not put a slash with the other one in here. That's because when you do like a mole balance, it's looking for the number of carbons in the molecular name that you give. So if you put that slash, at least right now, it's going to think that there's twice as much carbon in that molecule than what there is. So right now, both of these, if you try to do a hydrogen balance, for example, you would have problems with that. But for carbon balances, this should be fine. You just have to know that what it gets calculated as being propane or propylene is really the combination of the 2. And that's pretty much the best way to handle this if you have overlapping gases from your GC. Ideally, you would have a hardware setup that would be able to resolve all the different molecules, but if you don't, this is one way that you can set up your calibration gas so that you don't have any problems. So for the next part of this, we're going to start with the data analysis to actually calibrate what our data looks like. So if we go back into the File Explorer and we look inside of any of these folders, inside of these, we have a bunch of different FID data files, these different ASCII files, and those all pretty much look like the Peak Simple graph that I showed, and we need to go ahead and make some kind of calibration fit to the values for each of these peaks. So we'll close out of these. You need to have calibration gas that has all the different chemical IDs, and now you really need to have these elution times because it's going to use these elution times whenever it does the peak finding and integration. So make sure that you have these values entered exactly as they are here, at least with the headers, start and end. And then you need to run some calibrations on the GC or flow through some gases on the GC to determine what these elution times are. So here you can see that I used the Peak Simple component file to label out what these different peaks are and where they're going to elute. And that's a nice graphical way to come up with these elution time numbers, because now you can go into where you edit your component file and you can just get a printout of exactly what that looks like. So you can, I guess there's no copy and paste on this, but what I did is I opened it on two screens and I just copied the start and end values from the component file directly into this CSV file that I'm using for the calibration for Catalight. Now let's look at what calibration looks like. So we'll come over here and we'll open a Python editor. You can do this in command line too, whichever you would prefer. We're going to open up the run calibration.py module. And so this has, like with other things, it has two different functions in it. Get user inputs if you want to use like more of a GUI style interaction with it. And it's also got this main function if you want to use it for scripting. So we're going to use the GUI style interaction this time, and we'll hit run on this file, or you could call it from command line. And in a second, it's going to open up one window that's going to ask you to enter in the desired calibration file. So we go ahead and we find the file that I was just showing, and we open that. Now it opens up another window and it wants you to enter in the calibration experiment folder. This is a little bit different of a dialog window than what usually we work with in different GUI selectors with Catalight. This time it really matters which level of the folder that you select. So if I were to just select this folder, that's the higher level, it wouldn't really work out. What you need to do is go in and select the actual experiment folder that got run and just hit select folder on that one. Now it's going to ask you a couple of different plotting options. So this one's pretty simple. It just asks you what the figure size is. For these, there's a lot that gets put out in the figures. So it's better to select the largest size. You can go even bigger than this if you want to. And then for the fit, this is going to be if it includes the 0.00 on a fit, if you force the fit to 0. So you can go ahead and hit OK. And it'll show you the progress it's making as it goes through this analysis. And then you get two figures printed out that shows you what the calibration did. So here you can see in these top plots, as we go through time, or the run number, you can see that we're stepping through the different concentrations from 0, or low to 100%. And then if you look at these fit values, you can see that you get nice linear fits for each of these, except for where you have a couple of errors in how the peaks got integrated. And so these need to be looked at, and these are the peaks that kind of gave some trouble before. So even though if you look at the fit, it looks like the fit isn't awful, you can see from the run num plots that you need to go back and kind of reevaluate what happened with these. And that might involve tweaking your hardware on your GC to get better elutions, or fiddling around with kind of how the integration works in the base code. Now, all of this data, once you run it, is going to be saved in the experiment results tab. So if we go back, this is our experiment folder, and now we go into results, and now you've got the new calibration file, you've got what the readouts were for the concentrations, and you've got both of these plots in both SVG and in pickle format, so you can reopen it with the pickle format. And if we open one of these calibration files, now you see that it printed out the slopes and the errors, so now you have the fit parameters with the exact same elution times and everything that you were using before. So now in every other part of the code where you need to create a calibration data frame, this is where you can find the calibration data frame. This is how you make one, and you can import that into whatever you're trying to analyze next.